Yeah, thanks a lot. Glad to see so many people here. Maybe you came to the wrong thing, or maybe there are more nerds in Berlin than I was expecting. Maybe I would like to check about your vague knowledge situation. How many of you would say, experienced in using synthesizers? Okay. How many people of you know what a VCA is? Who has enough VCAs? Okay, no more. Enough VCAs.
Only 4.
Okay, well, that's not enough.
84 HP.
Okay. About 3 years ago, I learned about a project from a company that was reissuing an analog computer, and you could order one. So I did, and only had to wait for 18 months. So in the time before it arrived, I fell in love with other analog possibilities. That was Eurorack. And when this analog computer arrived, I found out that you can build almost any analog module on an analog computer. And I thought, why shouldn't it also work the other way around? Why shouldn't I use some simple Eurorack modules that only fulfill some basic functions that you can use to build, for example, an oscillator, a filter, an envelope generator, or anything that does something musical. 50 years ago, analog computers have been I would say in the last days of usage, and if you compare analog computers by the day with analog synthesizers, it looks a bit familiar. In both cases, you are patching the system. That means you're building your own machine. By connecting certain functions, you really build a unique machine. And in the case of analog computers, you do this to build a computer that will solve your specific problem. For example, you want to simulate the airflow around an aeroplane wing. You would build a computer that exactly does this one thing. That's why they're called analog computers, not because they work with analog voltage, but because they are built as an analogant to the problem you want to solve. And the technique 50 years ago that was used for analog computers was almost the same. I'm not an electrician, but I would say almost the same that was used for analog synthesizers. So it's not too big surprise that they looked quite similar. 50 years later, on the left you see the analog computer I was talking about that is available for educational purposes or for interested hobbyists. On the right side, I showed some modules that at least claim to be or are partial analog computers nowadays for Eurorack. They have at least some functions that can be used for analog computations, but maybe not every function you would need. The idea how an analog computer works is that you have a certain voltage area, for example, from -10 to +10 volt. And in this area, this area is defined as a range of -1 till +1 as your smallest or largest number. So you have to scale all your problems down so they can be modeled between -1 and +1. This has a positive side effect. For example, you can't leave your legal values, for example, by multiplying, because if you multiply two numbers in that range, you won't get outside of the range. Some other functions can leave the legal signal range, what you would call clipping in the audio range. So you have, if you are really calculating, you have to take care that you scale down your computation to not get into clipping. On the other hand, in the audio range, sometimes you want to get into clipping because that's also an audible, maybe desired effect. This, just to give you some ideas, this is, for example, how the patch panel of this Telefunken 50-year-old computer looked like. And it's not too unfamiliar, I think, with the view of Eurorack patch panel. This is a patch panel of the analog thing, the newer one. where we can have a better look at the basic functions that you would at least expect from an analog computer. One of the simplest operations that an analog computer can do is integrate, which is a bit surprising when you come from the digital world. The other functions are just summing, doing inversions, multiplying, and comparing two values. That's already it. With these 5 functions, you can start modeling almost any problem you want to solve. An analog computer is calculating not with numbers, but it's better to imagine that it's calculating with waves. So the result of your computation will look like a wave form. Typically, there are 2 possible scenarios. Either your simulation comes to an end. For example, if you simulate a pendulum or a suspension or so, it might oscillate and then come down to a certain value and stay there. Or it might simply continue oscillating. That's on the right side. And on the lower half, I showed you some examples where this is also used in the analog world, where you have, for example, an envelope that also is going on for a limited time, or you have an oscillator that is continuously running. So this is also quite similar. We don't have to read all through this, but I just wanted to show there are numerous documented applications in a wonderful free document in the net where you can see how you would build your own filter, your own oscillator, your own, what do we have, the phase lock loop or whatever. So the information is available. And of course, today we will only go to some simple examples. I will, after this slides, I will go through 3 patches where we can see live how this looks like. These are, again, the 5 basic elements I was talking about, and the symbols that you found on the screen before. And I will show you some examples of existing Eurorack modules that can stand in for these functions. At first, we have inverters. Inverters do something very simple, like on the scope, it's just flipping a wave upside down, like around the 0 volt axis. Don't confuse it with gate inverters. Gate inverters do something different because they only switch high and low, but this is really mirroring a function. It's like if you multiply by -1. And inverters are typically not as a single module available. It's more common that they are part of like a tools module or present at the in or out jacks of a module. Then we have summers. Summers are not to be confused with mixers, because mixers tend to more make an average value, so you don't get into clipping. With a summer or a precision adder, I mean modules that really correctly add voltages. So 1 volt and 1 volt will be 2 volt. Or to be precise, it will be -2 volt because they have the habit to invert the result, but you can deal with that. An example on the scope, when we are adding a sine wave and a square wave, then you get the precise sum of these two waves, as long as you don't get into clipping. On the right side, the most luxury precision adder I found was the one from Döpfer, because you can even switch for every entry. You can even switch if you want to subtract or add it, and you have the sum or the negative sum at the output. Next thing is multipliers. Interestingly, multiplication is quite expensive at least in an ancient analog computer, because there is no physical phenomenon that multiplies. But they found a way to misuse binomic functions, binomic formulas, to get a real multiplication. The example on the screen shows if you multiply 2 waves, for example 2 sine waves, you get a more complex wave, but you won't leave the area of your values. And I showed some example modules that can multiply. The best indicator is if the 4Q, which stands for 4 quadrants. This means you can really multiply any positive, negative values with each other. The module on the very right can't do that. VCA is a 2-quadrant multiplier, so it only can multiply a positive number with a positive or negative number. So maybe I should have placed some parentheses around this one. The other ones, for example, what I'm using is a quad VC polarizer from Döpfer that can be used to quite precisely multiply numbers. I was surprised that a ring modulator from Döpfer could not do this. Maybe it has to do with the fact you need always DC coupled modules, because you also have to be able to handle slowly changing or constant values. Maybe that was the reason, but the Döpfer ring modulator proved not to be a valid multiplier at all. But many other modules can do this for you. Then we need comparators, because we need to, as in every computation, you want to make a difference between two possible situations. And I listed here 2 kinds of comparators that I found. The first 2 are comparators that answer with gate signals. So they define gate signals like A is greater B or A is equal to B. Then if you use these, you have to think about what you're doing with this gate. So you would need the gate, for example, through another VCA or so to let's say, to make use of the outcome of the comparison. What I found more comfortable are the so-called voltage controlled switches. The one on the right is, of course, has 8 comparators, so it's the luxury variant of the one before here. In a voltage controlled switch, you have a control voltage that decides which of 2 possible connections will be made. For example, you have 2 entries and one output, and the control voltage decides if the upper or lower entry is going to the output. It can also go the other way around, so you can also switch one entry to 2 outputs. And the last one are the integrators that you need, and I only found one for Eurorack, and it's not available for too long. I think about a year ago or so it was introduced. This is a real integrator. Sometimes slew limiters are also called integrators. That's yes, they have one inside, but they do a bit more, and that will more disturb your pure integration purpose. So this is the only one, at least I found. The screens on the right try to show what happens if you load or unload an integrator. Maybe the basic idea of an integrator is it has a certain state. An integrator can have a certain load. It can have a value of 0 volts or of plus 8 volts or of minus 3 volts. And by loading or unloading the integrator, you slowly change that value. So the integrator is the only element of all of these with an internal state. And this means it's the only element that can do things in time, because you slowly can load or unload it. Every other function, like adding or multiplying, happens in an instant. So that you can't model anything in time with them, but if you have an integrator, then you can, depending on how fast you load it or unload it, you can really do things in time. And of course, to get some waves out, you want to do things in time. I've showed 2 examples where the upper function shows if I'm loading with a positive, like let's say +1, or with a negative value, like -1. And in the upper example, the integrator just got into clipping. So it was at, let's say, +10 volt. It can't go higher, so it will stay there. And if I start unloading it with -1 volt, as can be seen here, it goes down until this doesn't have to be the negative maximum, but in the area. So this can be the outcome if you send any gate or any square wave into it. The lower example shows maybe if you want to build an oscillator, the ideal case where you exactly turn around with your oscillation at that moment when you reach the ceiling. So some other things you might want to have or should have are some voltage sources, some attenuators, maybe an amplifier to amplify some signals. And it's always nice to have a scope. And if you want to do some calculations, you want to see the results, not only listen to them. So a scope is, of course, also on your wish list if you want to do something like that. I wanted to give a short overview where we are in the modular world here. So I started with most complex or comfort modules that may offer you lots of functions, maybe hidden in a menu system or so, that can do a lot of things, but that are hard to be used for any other purpose than they were intended for. Simple modules, for example, would be something like an envelope generator, a simple oscillator, whatever. The next level where we're getting a bit less comfort but more flexibility would be I know it from search, modules that have to be patch programmed. So you buy a module that has some basic functions, but you have to connect them to get a meaningful function out of the module. This is already quite close to what I'm talking about today. Then comes analog computing, with the elements I just showed. And below that, the only thing that comes to my mind is like if you solder your own modules also. But since I have no idea about electronics, for me, it's this analog computing approach is the only level that I can go to, and I can't break anything. That's good. So this was for about a year or so my field of interest. So since I have patched something already here on the rack, I made a picture just to have a view of all modules I have in the system. Only about half of them is really made for analog computing or installed for analog computing. The others are some basic modules like a filter or an oscillator or so, because I, of course, need to do anything meaningful with the whole system. Here's a closer zoom at the, let's say, at the analog computing core. And with these modules, for example, it's possible to build oscillators, filters, or envelope generators, anything that comes to your mind. Why is it so? Because computing means just everything you get out in the module world, like for example, a waveform is the result of computation. It's nothing else or nothing special. If you have a sine wave or a rectangle wave, or if something filters something out, or if something changes the loudness, this is all the result of computation. And these modules are all you need to compute. So from now, I would like to show 3 examples, which with hopefully an increasing level of usefulness. This is a simple quadrature sine oscillator where you just have 2 integrators and an inverter. So your signal comes in here, gets integrated once, integrated another time, inverted, and then just fed back. And I copied this right from Wikipedia. This is if you do something with a signal that does just this, then the energy lowest fulfilling wave that would do that is a sine and a cosine. So this shows maybe how an analog computer works. If you switch on the power, it will find a solution of some waveforms for your system that just fulfill your circuit. So this is maybe the hello world program of analog computing. It will just spit out a sine and a cosine, like 90-degree phase shifted signal. I will remove some cables here now, and then we can just try it out, how this would look like. I will have to remove my previous patch here. The upper half of the system is patched with kind of an analog shift register just to replace a sequencer that I don't have here, so that we can at least listen to some alternating voltage levels or frequencies in the end. But the basic patch is quite simple that I'm going to show you. So. So I'm taking these are the integrators as can be seen. If I take the output of one integrator and send it to the next integrator and do this again, the output to an inverter, which this model is, and the inverted output back to the first integrator. In principle, I already have a sine wave generated. I will send it to the scope. Hopefully. And oh yeah. So here, at least on the rack, you can see now that we have two 90-degree phase shifted waves, and if I change the amount that comes into the integrators, I can alter the frequency. Problem is, sine oscillators are quite delicate to operate. If I go a bit out of the range, it will fade away. So with this simple patch, it's only possible to have a sine wave in a quite limited range of about 1 or 2 octaves, and you have to take some further measures if you want to have a stable sine. But this just should serve as a first example. Also, maybe I can it be seen good there? I have to. Yeah. Sorry, I need to go to my scope. Because so that's what I want to show here. And an interesting thing is if you have two like a sine wave and a cosine, if you use both signals and interpret one as the x-axis and one as the y-axis, then you get something like a circle. This can be used for more complex patches, where you modulate things on it, but I will show this in the third patch in a moment. But this is the basic idea that you have an x-y mode where you can interpret one direction as x and one as y, and it would look like this. Okay. So, the next thing I would like to show is how to build a triangle core oscillator, which is a bit much more stable and also a bit more interesting in the way how you can extend on it. So let's get rid of this. So the idea of a triangle core oscillator is, as I showed some slides ago, the idea is that we will load. maybe, yeah, thanks. The idea is now that we, for some time, we load the integrator with a positive value, and then for some time we unload it again. So meaning for some time we are giving a +1 signal, and then we are giving a -1 signal, and so on. So this means we have one waveform that comes in as a square wave, and the result of the integrator will be a triangle wave. And why is this working? We have a comparator that decides if we should give +1 or -1. And the comparator is just looking at the outcome of the current integration value and subtracting its own output. This is a simple feedback loop that will just take care that whenever we hit the ceiling, we just switch from +1 to -1. So this means we are getting two waves simultaneously out of this simple circuit. And yeah, let's patch this. I don't know if it's good to be seen, but I put this value to a positive, or this output to a positive value, and this output to a negative value. So we will just take these two outputs in the switches. This is our +1, and this is our -1. Then I will take this cable, and the result of the comparison will go into our sum, and I don't know if you can see it good, but it is inverted. So this is the one that was inverted on the slide. And then we take the output, the result of this as the input. Maybe we could show the slide after I finish this, that you can compare it. And let's try to come out. So now, just if it's possible, that you try to make the connection. Maybe that's not, that's not too obvious, but maybe if you look at the video later, you can confirm that I just patched exactly the connections that you see on the slide. So at least the scope is telling that I did so, because now we have the two waveforms I just mentioned. And again, if I change the value that, or if I attenuate the amount of voltage that goes into my integrator, I can just change the frequency. Because now I'm loading the integrator slower, and now I'm loading it faster. So this is already a triangle core oscillator, and compared to the sine oscillator, you can see that I can almost go through the whole range and it stays stable. The amplitude stays stable, and yeah, I have many octaves available. This is why triangle cores rock, as they say. Then we can go one step further. This is what I just showed with an attenuator that's already built in. I can just change the frequency. And now let's say we want some voltage control over the frequency. We don't want to turn it with our hand. So what we do is we could use, of course, a VCA, but one of our simplest modules that we already have in this basic set is a multiplier, and the multiplier is something like a super VCA. So why not use a multiplier at this point? This means that we take the square wave and multiply it by our intended frequency, which just means that we reduce or increase the square wave height, and by that we will do this thing that I'm doing by hand now automatically. So let's take this signal and put it into one of the polarizers, maybe here. The output would then go back to the integrator. And now we, of course, we need some voltage, some control voltage that should define our frequency. And on the upper half, I made something that is about an analog shift register that just gives me some alternating values. So I don't need to have a sequencer or so. And if I just, you have to believe me on that. And if I just take the output values from them and use them as multipliers, then, and maybe, yeah, I have to adjust the values here a bit. Then you can see now is, now we're having like automatic frequency changes. Maybe now we also want to listen. Don't expect any audio goodness, it's just to confirm that the waveforms are there. I have to be louder. Okay, please don't start dancing. So, oh.
Can you switch the image on the big scope link? On the big scope.
Oh, yeah.
You left it on the.
Sorry. Yeah, that is a bit of a disadvantage on our setup here. Yeah, this has to be reset. And it's rewriting the scope. It's not seen. Yeah. As the auto set is a bit confused because I'm constantly changing already the frequencies. So maybe that's you can see the waveform sometimes, but the scope has difficulties to zoom in here.
It will stop this sequence.
Yeah. Someone with experience in operating the scope for me? Okay, then I will have to walk back and forth a bit. So, just put this one out and give it a like a positive value. I will just put it back once, so that we have any kind of signal at least. Okay, that's at least half of the signal. Now we have it. Okay, so, and now I will try to change it only slightly, not to confuse the scope. Yeah. Maybe also get the signal. So if you show the scope on the screen, then I could check if. Yeah. So then let's just. Yeah. I think that's about as good as it gets because the scope constantly has to adapt to the different. It doesn't find a good syncing point. You can see the waves at least, and yeah, for the rest, I will have to let you see the on my rack the smaller scope because this is because this is better. Better equipped to deal with the changing frequencies. So it's a bit better to take in the lower frequency domain. Does it show anything valuable here? Or, yeah? Let's say together with the sound, you get an impression. Okay. So there we built our own triangle core oscillator. What could we do next? We have computing elements. We can, of course, do anything that comes to our mind. One simple idea is why not make a Sawtooth oscillator out of it just by adding another multiplier? Because on the upper half, I show you again, we have the two waveforms we also have is the triangle and the square wave, and the triangle is always raising when the square is high and falling when the square is low. If we multiply these two waveforms just with a multiplier, what will we get? If we multiply by +1, the curve will stay the same. So this one stays the same because multiplication with 1 is just identity. If you multiply with -1 at this point, it will be flipped around. So the falling curve will become a rising curve. So what we get is a sawtooth at twice the frequency in this case. So let's try it out. Let's pick up, let's say from here. And just see one way from here. So it does not look too beautiful right now because we have to adopt a bit. I will for this I will remove the alternating frequencies maybe, and just go to some constant value, and you can better see it. And I will just adjust the waveforms a bit. The scope has a hard time syncing. I will try to switch the both inputs. So, and that's live wave shaping. Okay, I think we are in the area of sawtooth wave. And maybe, is this the right one? No, it's also. Just your bass. And maybe. So, no reason for dancing, but this is at least a working Sawtooth oscillator. And of course you have to do a lot of fine-tuning because things are not so precise as one would like to have them. Another thing we could do, but I won't do on this system, but I can show it on the other system after the talk. We could also build a through-zero oscillator, which is, I think, a very cool thing. With a through-zero oscillator, you can play negative frequencies. Many of you maybe have heard of it. Of course, there are no negative frequencies, but through zero core oscillator will react to negative voltages also. Typically, if you give an oscillator the command to play like a -1 volt pitch, it can't do that. But with through zero, you can just flip the waveform upside down. Can a bit be seen already on the scope down there, but let's talk about this maybe after this official part. But this is just one further possibility. Basically, if you can patch your own oscillator, of course, there are no limits. You could get the idea, why not build a filter into my oscillator, or why not have some kind of other modulations inside it. This here shows, for example, how beautiful a through zero oscillator would look on a scope, because that's that's not my laptop, so I can't zoom in here, but on a through zero oscillator you see that you have a falling sawtooth until you cross the 0 hertz frequency area, and then your wave flips upside down. You have a rising wave until you cross 0 again. So this means you won't get into any clipping or go to any barrier, but you can go right through 0 volts. I found that quite interesting to patch. It's a simple patch anyway, but it has. We can later listen to that. It has some interesting effect if you just go through 0 hertz. So you can say you can listen to frequencies, or you can listen to sounds whose average frequency is 0 hertz, and still hear something. Okay. The last patch I would like to show is Chaos Oscillator. This is from the Analog Paradigm website. They have lots of schematics there. I took the simplest one, or one of the simplest ones. And for this one, this is not so easy to patch, because you have to do some more precise feedback, and I need an absolute value function. So I'm cheating a bit. This means I prepared something, and while I'm patching this, you can watch that I'm making not too many mistakes, because already one would be too much. I tried yesterday, and it took about 5 minutes. So typically this is what everyone in the synth business avoids, like live patching. Let's see. So, to be very secure, I had exactly the same cables. I hope I don't miss one. So, let's start from the very right. And I have also to take care of the switches. Yes. Okay. But I can, while I'm patching it, maybe I can try to tell something about chaos oscillators anyway. The idea of chaos oscillators is that you have, at least you need 3 integrators. And each one is representing 1 dimension, so they are at least 3-dimensional. And you're sending a waveform through 3 dimensions. Sorry, I think I have to pay more attention to the patch. So. That's not what I wanted to see. Oh yeah. Okay. So, what maybe does not look too exciting, I just showed you the cycle that you can see if you have a sine and a cosine wave. And now we have a more complex waveform. that can be tweaked with various ports on the system, and I'm trying to get a bit more interesting shape before we try to listen to it.
Can you switch the main source code to the...
Yeah. Yes, I will. I will. Just a second. Well, because that's the main reason I bought this one for the chaos patch. Yeah. Square wave don't look too thrilling. Let's maybe do it. So let's keep it about that way because the dimensions may vary, and maybe also. Yeah. So this is giving, at the moment we are not having any altering pitches. I will try to, everything okay? I will try to give at least a bit more variation here. Let's say, this is SCV. And what I have to find out where the freedom grades are. Like some rulers or some knobs are very delicate and they will lose the oscillator quite soon. So it will break down. It will experience the worst thing that an oscillator can experience, a steady state. But yeah, this one looks like I have lots of freedom here. Yeah, in a certain degree. So we could now use this entry as our modulation entry. So I just steal the cable, put it through a VCA, and get another cable. Yeah, if it's hitting any ceiling, of course it sounds. I will do something else with the signal. I will raise the control voltage level a bit. So you see, you can get all kinds of ugly sounds with a chaos oscillator. Interesting thing is that it's completely or almost unpredictable how the waveform will behave, but in difference to random effects, a chaos oscillator at least circles the same orbit after a while, and so you have you have a sound that will never be predictable, but it will also not leave a certain range at least. Is it still visible also there? No, not now. We lost the chaos territory. Yeah. it's very hard to get the sweet spot where you have a certain range where you can modulate without destroying your oscillator. This makes it a bit hard, but if you find a good sweet spot, it looks quite nice and it gets quite a rough sound. And it can even happen that it dies away in a way that I really have to restart one oscillator, that I have to press pause and restart again, because otherwise the cycling won't get going again. Okay. Let's keep it this way. So this was the final example I wanted to show for patching. Yeah, then I would say thanks for your attention. I hope it was not too confusing or too well. I hope you did not expect more sound goodness. What I wanted to show is not that how square wave sounds or so, but that you can really build your own. That you can really build your own oscillators, your own. Filters or whatever we saw the schematics for with some simple patches. If you have let's say a certain quantity of 5 simple different modules that are besides the integrator that are widespread available, and the integrator, well, at least there's this one that I know of. Yeah, then thanks for your attention. And
yeah. Thank you very much. That was really interesting, and I'm sure we are all thrilled to try it out ourselves.
Yeah.
As you said, there's another computer down there to play around for you. Maybe people are.
Maybe get off your seats, flood the stage, or flood me with questions or what. I don't know if it was maybe too confusing or too I left too much things out because I didn't take notes for the talk. Yeah. Anyone?
Yeah. I'm curious about the integrator because it's harder to get. You said that for the multiplier, for example, you probably the limits is around the coupling. That's not EC. It's AC. What exactly is the limitation? Because for getting slew as integrators. Not precisely because of the but because the surge generator is described as an integrator. But
if you go to the Döpfer page of the Döpfer slew limiter, you just the second word is a slew limiter, aka integrator. It says there. That's a kind of a nickname of the module, maybe in the modular world, but it is not an integrator. It does more. The slew limiter has already some built-in feedback because it wants to get slowly to a destination value and then stay there. And as far as I know, it's hard to get the feedback patched out again. So it does too much already. This is why slew. You can build all oscillators with slew limiters. If you, I made a Modular thread on the topic, and someone posted there that he did so. He used 2 slew limiters and a kind of shifting inverter. And that gives you some kind of oscillation, but it's not like, it's a bit like if you use a mixer as an adder. It will add, it will do something addish, but it's not real adding. And so I would not recommend, at least I had no success with using slew limiters to get sine waves out of them.
This is also true for the surge.
Despite the one slide, I have no surge modules on my own, so I cannot tell about these. There may very well be modules on the market that can really also integrate. The Mars module has an integrator symbol on an output, where a YouTuber said, if you know the meaning of that symbol, please post me in the comments. It was an integral. But I think it's not real integrating because it looks like it can only handle positive values, for example. but I'm not too sure. What I'm quite sure is that the mass module, for example, can't multiply, at least not as a 4-quadrant multiplier. So you could not multiply arbitrary positive or negative numbers, and it doesn't have a comparator. So even if it's a cool thing, surely, but it's not a full analog computer.
I have more questions, but just one more.
Yeah.
You said that the voltage-controlled switch was used as a comparator. I don't know if it was used as a comparator or as part of a comparator because it was not clear how to do that.
I switch back to there. It is, you can really use it as a complete comparator. Let me just find it. Let's have a look at the schematic of the comparator. This schematic means that you have two signals to choose from on the left, and typically two other A and B that are subtracted from each other, and then the difference of A and B will select the upper or lower input and let this one through. Let's only talk about this direction, the other is also possible. And for this purpose, this dual VCS from Döpfer that I have already also in my system does exactly this. So you have control voltage. It doesn't you don't have the difference between A and B. You have to calculate the difference on your own. And that's what I'm calling the control voltage. And it's a pity it doesn't switch at 0 volt. It switches at 3-ish volts or so. And for some purposes, you have to adjust for that. I brought this in my schematic here as the offset here, but I did not use it. Typically, you would have to add an offset so the switch will really switch at 0 volts and not at 3 volts. But I found out by trying that it doesn't matter so much for this simple kind of oscillation. But to explicitly answer your question, I would say yes, the Döpfer switch is real, can be used as besides the offset necessity, you can use it as a real comparator. The other ones, maybe I was also rushing there, the two ones on the left, they compare two values, but the result will only be a number of gates, like the gate signal 4 is greater than or is lower than, and you will have to take care of the gate then. For example, use it in a VCA or by some other means to, in the end, then select your signal you wanted. But the advantage, at least as far as I know of these two here, is that they switch at 0 volts. So you have, there's not the perfect switch module available, but you can get quite close. Yeah.
Thanks for your presentation. I have a question regarding noise. So as I see, like in your computation, you have multipliers. I presume that multipliers are very susceptible to noise. And that means that perhaps there is a limitation to how complex computation you can do without improving the SNR or like any other sort of error correction. So have you found these limits?
I did not measure them out by any means. I'm quite sure that you're right, that the multiplication results will not be like a mathematically precise multiplication, other than on a real analog computer. It will be in the area of you multiply two things, meaning that the higher one gets, the higher the product gets, etc. But it's if you would really measure out your multiplications, I'm quite sure they would not be that precise in the Eurorack domain.
In terms of like practical application, you haven't seen like any bottleneck?
No, not for my purposes, but I only had simple purposes until now. I just thought when you mentioned noise that you would want to ask that. There are also noise patches available. You can also get, you can even patch your own noise generators, but that's a different topic. Yeah. And maybe this would explain. I found that it's, as I mentioned, it's hard to control the sine wave. It quickly falls down if I change the voltages, and even if I add two multipliers, so that before each of the two integrators I lower or raise the frequency. Even if this, what works on an analog computer seems not to work here as well. Maybe that is because of the noise and the multipliers. It might be an explanation. Yeah. Any questions?
Yeah.
Yeah.
In terms of like more complex patches, have you found that the amount of modules you need scales? Like you need more modules to make more complex?
Yeah, of course. If you look at any schematic, where do I get one? Wait, let's take this one. Of course, the number of symbols in a schematic will almost tell you the number of modules you would need.
Yeah.
Maybe there are modules with 2 comparators, but yeah, of course. And I would say, let's put it this way. I'm not doing this to save on money, which I don't, and I'm also not saving on rack space. You don't. This is just for fun and no profits. Of course, you can argue if you want to build a real complex oscillator with really nifty features. You can do this, but it's of course it will take a lot of rack space, and it's only for scientific or nerd purposes. Yeah, that's true. Yeah, it's like on an analog computer. The cool thing is it won't if you do some calculation and maybe you want to do something your system can't do, then you're not able to do it. In a digital computer, you could say, well, I can do it slower. My graphics will stutter also, but it will still work. In the analog world, if you're missing only one element, then you're lost. You cannot do it. But if you buy the element, then you're as quick as before. You're as fast, and you're not limited. So there's no slowdown. Yeah, regarding scaling. But yeah. I think this I think this is a reasonable system that can give let's say a good amount of entertainment. If you really would want to build complex oscillators or anything, yeah, you would have to invest quite much.
Thank you.
Yeah.
Can it run Doom?
Sorry.
Can it run Doom?
Can't. I tried. Or you have to interpret some very easy scope signals as a graphic, but no, it can't. Yeah. Last chance. Pila, you have some question. Yeah. Then maybe if you like, we can just a bit go closer to the systems up here or on that one, and we can just play through some things. On the lower system, I did implement a through zero oscillator that I was talking here about so much. You can see, and you can also listen to a through zero oscillator, and it sounds a bit more interesting than the very simple things here. Because it's a nice effect when you have a frequency that goes lower and then it hits through 0 hertz and comes out on the other end. It sounds quite interesting if you have some FM modulation on it. So maybe if you like, stand up, come to the systems, and let's tinker around.
Yeah, we get a drink and
yeah. Okay, then. Thank you.